In this example, we're going to consider an object which is projected into the air at an angle. And so an object is projected into the air with an initial speed of 70 meters per second at an angle of 30 degrees. And we know the object undergoes projectile motion, which means it's going to have a curved path. We want to use the figure that's provided to represent projectile motion, and it says as we did in class. And so essentially we can conceptually analyze what's going on in terms of this projectile motion by using the figure that we have and thinking through how the object falls off of that straight line path. And so we're actually not going to use a ruler or convert anything, even though it says that in this description here. So in this particular picture, and on the next slide it's much bigger, we have a projectile, and the line that's shown here in the picture represents the motion that the projectile would take if gravity wasn't present. So if you were to shoot something in the air at an angle and gravity wasn't present, the object would continue to move in a straight line path, basically keep going forever and ever and ever, right? Because there's no gravity that's present. So this is a picture of what would happen if gravity wasn't present. The dots on here are separated in 1 second intervals. So if you shot the object at 70 meters per second, the object would cover 70 meters every second that goes by. So this line on here, the separation between these dots is a distance of 70 meters, or basically approximately 70 meters between each of these. Now it's hard to see in this picture, and we'll sort of see it on the other picture when we can blow up the screen. So in order to represent projectile motion conceptually, we have to draw this picture that represents the way that the projectile would move if gravity wasn't present. We have to put dots on here that represent the position it would be every second that goes by. And then we have to create a table that shows how the projectile actually falls off of that straight line path every second that goes by. And so we can use the formula, and my slide got messed up a little bit here, that the distance that an object falls every second is 1/2 gravity times the time squared. So for the first time is 0, the distance is 0. When we go to 1 second, the distance that the object falls is 1/2 gravity times time of 1 second. So 1/2 of 10 is 5. 5 times 1 squared is 5 meters. After 2 seconds, the object falls 1/2 gravity times the time of 2 seconds squared. So 1/2 of 10 is 5. 2 squared is 4. 5 times 4 is 20. And we can keep doing this for each 1 second interval. So after 3 seconds, the object falls 45 meters. After 4 seconds, it falls 80 meters, and so on. So this is actually the distance that the object would fall if it had been dropped. So after 1 second, it would fall 5 meters. After 2 seconds, it would have fallen 20 meters, and so on if it had been dropped. And we can use that information along with our picture to make a representation of projectile motion. So as I mentioned, so this is a blow up of that picture. Each of these dots are separated by a distance of 70 meters because our projectile was shot at 70 meters per second, and it will travel a distance of 70 meters every second if gravity is not present. The angle here, although it's not actually indicated in the picture, is an angle of 30 degrees because that's the angle that the object was shot. So the dots on here represent where the object would be in these time intervals, equal time intervals of 1 second. So this is 1, 2, and so on. And each of these separations are 70 meters. We can go to our table that we created on the previous page, and we can see how far the object falls vertically off of that path in these time intervals. So after 1 second, it falls 5 meters. Each of these blocks in here, it represents 10 meters, so it falls 1/2 of a block. After 2 seconds, up here, it falls off of that path vertically 20 meters, so 2 blocks. After 3 seconds, it falls a distance of 45 meters, or 4.5 blocks. After 4 seconds, it falls off of that straight line path 80 meters or 8 blocks. The next one at 5 seconds, it falls a distance of 125 meters or 12.5 blocks. After 6 seconds, it falls 180 meters, 18 blocks. And then finally, when I get to 7 seconds, it falls 245 meters vertically, which is 24.5 meters. So, 24.5 blocks. And so I made this nice and easy so that it would all work out in my picture. And so now I can connect the locations of where the object actually is in terms of falling off of that straight line path, and that shows me the projectile motion. Now, the next thing I can do is I can determine the range of the projectile, which is the distance that it travels from where it starts to where it ended in terms of that horizontal distance. And I notice on my graph here that that distance is 420 meters. I can also measure the maximum height, which occurs basically at the halfway point here, so at the 210. It's exactly halfway. That maximum height occurs, and it occurs right at this position. And so if I follow that across, it's a little bit bigger than 60, so I'm estimating it at 61 meters. So from this particular representation, we really only had to do some very basic math, and we could use this graph to measure the range and the height of the projectile and show this projectile motion. We're getting a little bit ahead in the question, but we could also use the range formula to determine the range of this projectile. And the range formula says that the range is equal to the initial speed of the object squared times sine of twice the angle divided by gravity. The initial speed is 70 meters per second, so I would need to square that, times sine of twice the angle, which is 30 degrees, so twice 30. And then divide by gravity. When I square the 70, I get 4,900, and then the units are squared as well. And then I'm going to take sine of 60 and then divide by gravity of 10. And when I put that into my calculator, I get 424 meters. So on the previous slide, the range was measured to be 420. And so, it's just a little bit of an approximation with that picture. And so the range formula is giving me something very close. I can also determine the maximum height. So the maximum height is determined by taking the initial speed squared times sine of the angle squared. So I'm going to figure out what sine of 30 is and square it, and then divide by twice gravity. So if I were to write this or put this into my calculator, I would put that as the speed squared, 70 squared. I would calculate sine of 30 and then square it, and then divide by twice gravity. 2 times gravity is 20. The speed squared is 4,900, and then I would take sine of 30 and square it. And when I put that into my calculator, I get 61.25 meters. And that is very close to what we saw on the graph. The other part to this particular question asks a lot of conceptual information about the projectile motion. And so we want to know, does the horizontal velocity of the motion change? Does the horizontal velocity of the object change during the motion? If so, how does it change? Does the vertical velocity change? Where's the velocity a minimum? When it is a minimum, is it 0? What's the magnitude and direction of the acceleration during the motion, and so on. So there's a number of different questions. So this is actually just a representation of some object, and this is true of any object that's shot into the air at some angle here with some velocity. So this vector here represents the initial speed of the object. So it turns out that we can resolve that initial velocity into a component that's horizontal and a component that's vertical. Now I've chosen numbers here to make this easy to see what's going on, but these numbers are not always 20 and 40. This is simply something to give us some idea of what the motion would look like with easy numbers. So this is where the object is at time t equal to 0. Remember, it's shot at an angle here, and this is the velocity that the object has along the horizontal, and this is the velocity it has along the vertical. After 1 second, the vertical velocity has decreased by a factor of 10 because the acceleration that's present here is the acceleration due to gravity. And the magnitude of that acceleration is 10 meters per second squared, and it's directed downward. And because of that acceleration, the y, or the vertical velocity, is decreasing when it goes up, and it's decreasing by 10 meters per second every second. However, the horizontal velocity here is still staying the same, and it's still 20. After another second goes by, the vertical velocity has decreased by another 20, and the horizontal velocity stays the same. Again, the vertical velocity decreases by another 10. The horizontal velocity stays the same, and then we reach the very top of the trajectory. At the top, the vertical velocity is 0, but the horizontal velocity is still present, and it's still 20 meters per second. So at the very top is the location where the velocity is a minimum, but it still has some horizontal velocity. The vertical velocity is not, the vertical velocity is 0. As it falls back down, you can actually just reverse the direction of the vertical velocity, and the picture looks the same. So after another second goes by from the top, now the velocity in the vertical direction is starting to increase in the negative direction. So it was 0, and now it's 10. Horizontal velocity is still the same. As it falls, the vertical velocity increases by another 10. Horizontal stays the same, and so on until it gets back to the position that it was launched at horizontally and vertically. Not horizontally, but vertically. And so you'll notice that the vertical velocity is the same as it had over here, and the horizontal velocity is still 20. So throughout the motion, the horizontal velocity stays the same. The vertical velocity is always changing. On the way up, it's decreasing. On the way back down, it's increasing. In terms of the distance covered every second, along the horizontal direction, the distance covered every second is the same because it's traveling at the same exact velocity every second horizontally. It's always 20, which means that every second it covers 20 meters in the horizontal direction. The distance covered every second in the vertical does change. So on the way up, you'll notice that the distance covered every second keeps decreasing. So if I imagine these steps, right, that I would be drawing here, you can imagine the steps. There's a big step in the beginning, smaller step, smaller step, smaller step. So the distance covered is decreasing on the way up, but then I draw my steps going down, and the distance covered is getting bigger. My steps are getting steeper, if you want to think about it that way. So the distance covered every second on the way back down is increasing.